Other questions?
One that.
Okay.
Earlier we said, I think a couple of classes back, that the location of picture changing operator will not matter under certain condition.
Yes.
And later we realized that one of these conditions is boundary.
Yeah.
Which I think can be interpreted as a fact also, that picture changing operator should not be at the boundary. I'm not sorry, the boundary term should not appear in the d omega.
Exactly.
Right?
Yeah.
One thing is that. But if I ask about the location of the picture changing operator,
yes.
Are there any restrictions on that? For instance, there was one condition that they should not collide, otherwise they will lead to this speed.
That is true. Yes.
And you said something about the spread of picture changing operator also, right? That they should be independently spread in the modular space, something like that.
If they're independent of the modular.
They can be. Yeah. Meaning, a priori, you can choose the picture changing operators anywhere. I mean, the proof that we gave, right? Up to boundary terms, it doesn't matter where you put the picture changing operators. Right? So we'll see what are the other restrictions. They shouldn't collide because then there'll be singularities, right? So you have to avoid those as well, right? And yeah, so we'll see how to fix those, right?
They should not collide with the vertex insertion.
Yeah, they shouldn't collide with the vertex insertions and so on, right? So you have to avoid those regions, right? So these are separate problems and you have to deal with them separately, right? So we'll discuss the boundary problem today, right? And then maybe next time on Thursday we'll discuss what happens on they collide. How to avoid it.
Reduced PCO. You said that these Y alphas. You can, I mean, you said it as an assumption that you should take them to be independent of the moduli space parameter.
If you take them to be independent of the moduli space, yeah, exactly. Then the extra term drops out. Now that is no longer necessary, right? Because once you include the extra term, you can take them to be dependent on the moduli parameter.
In what we have done so far, is it anywhere visible why the heterotic string had to be SO32 or E8 cross E8 or so far?
Well, so far meaning I have not proved it, but that I stated it that modular invariance forces it to be either SO32 or E8 cross E8 of the torus amplitude, right? That on a torus amplitude, it shouldn't matter whether you take, if you replace tau by A tau plus B over C tau plus D, where A, B, C, D are SL2Z matrices. Yeah. Exactly. You'll see that. Yeah. That you are supposed to integrate over tau, right? And normally you show that you take integrate over the keyhole region, right? And that is under the assumption that the integrand is independent, the invariant under tau going to A tau plus B over C tau plus D. Right? But if that is not the case, right, then you lose that whole picture. Right? And I indicated why this is the case, right? Because this sum over the charge vectors, right, take value in particular lattice. So no, charge is quantized, so you have to take value on some lattice, right? Whether it's 8 cross 8 lattice or SO32 lattice, charge, normal electric charge, it takes value on a lattice. In our world, right? What is that lattice? One-dimensional lattice of integers, right?
Quantized in units of
E. Exactly. Otherwise, one-dimensional lattice with basis vectors of length E, right? So charge vectors always take value on a lattice. Okay? So you start by saying that, okay, let's assume that the gauge group is something where the charge vector takes value on some lattice. You don't even need to talk about gauge group, right? It's the internal momenta, which appears as charge from the space-time viewpoint, right? This is the internal momenta, right, which are not part of the 10-dimensional momentum, right, but extra 16, right, which, as we discussed, I mean, you only have to have the left moving ones, but not the right moving ones. Okay? Then you say that they take value on some lattice, right? You don't know what that lattice is. Okay? And then you find that the consistency requires that that lattice has to be either the SO32 mod Z2, what lattice? Yes, that's true.
There are many possibilities.
Yeah, but again, there are, once you compute the one loop amplitude, right, you will find that of those many possibilities, only 2 are allowed. Yeah, so they are equivalent because as a CFT, they are choosing a lattice on the for the scalars is equivalent to deciding what kind of GSO projection you will have done for. space.
Since the amplitude was constructed from, let's say, physical states, all these insertions were BRST closed, right?
Yes.
Like vertex operator insertion.
Yes.
And if you insert anything which is BRST exact,
Yes.
this picture changing operator, the 90 would think that this would be anyway, but does not matter. That the insertions of this BRST exact operator would not matter in the amplitude, right?
Should not matter.
Yeah. So this argument also kind of holds right now. I mean, apart from the fact that we are showing the boundary term is just 0.
See, if the boundary term is okay, logic goes in the following way, that we want this to happen. That if we insert a BRST exact operator, it should give you 0. Okay? If the boundary terms don't vanish, then it doesn't give you 0. Right? Then there's a problem. Right? So this is something which we desire, but it's not proven, right? That so for consistency of the theory, you have to prove that this is what happens, right? That if you insert a picture changing, if you insert a pure gauge state, exact state, that it should decouple from the amplitude.
That statement is not correct. Right? I is not quite BRST exact in the small language.
Okay.
No, which is not BRST exact? No, picture changing operator is not BRST exact. But the vortex operator, if you can insert a vortex operator which is BRST exact, right? That's what we showed last time, that it gives you a total derivative term in the moduli space, right? And then the question arises whether the integral of that vanishes, right? And we saw that it vanishes up to boundary terms. Is this clear? Any other question? Okay. So today we'll discuss some examples of BRST exact states. Okay. So take massless vortex operator, and we'll proceed by assuming that the boundary terms are 0, right? Later on, we'll come back to the boundary terms. So massless vortex operator. Okay. And we saw that at generic momentum, these vortex operators take the following form. So this is physical for a square equal to 0 and a mu zeta mu equal to 0. Okay. By physical, I mean BRST closed. Now take if zeta mu nu equal to, let me call it V mu A nu with A dot V equal to 0. V is some vector which satisfies A dot V equal to 0. Then there is an exercise that V is proportional to okay, here QB, okay, only the anti-holomorphic part of QB is relevant for this, because the holomorphic part I have kept exactly as it is, C to the minus phi psi mu to the ik dot x. Okay. The anti-holomorphic part, okay, had a C1 L minus 1 term, right? That term acting on, sorry, C tilde 1 L tilde minus 1 term. Okay. That term, C tilde 1 doesn't annihilate this because C tilde has gone away. Okay. So C tilde 1 L tilde minus 1 term basically brings down a K mu from here. Okay. And K mu del x mu, and that's what produces a term like this.
You wanted to say zeta mu is this form, this is BRST exact form.
Exactly. So this means this is BRST exact. So this implies So this is BRST exact. So it decouples. Is this clear? Same V, yeah, same V. Yeah, because I have taken zeta mu nu to be this, right?
That V is technically acting with QB or something.
No, no. If I act with this, right, we'll get a state like this with zeta mu nu given by V mu k nu.
This V is yeah, okay.
Yeah, this V is that V. I mean, was there any other V? No, small V. This is small V. Yeah. Okay.
V is from the space-time viewpoint bosonic. That's why the writing writing. What are you doing?
No, V is bosonic, yes.
Fermionic vertex operator and wanted to show BRST exact.
Yeah.
I have to write it as what exactly? QB something commutator.
Which is Grassmann odd.
Yeah.
Oh, here, yeah. See, the point is this was bosonic, right? This is Grassmann even. But this is Grassmann odd. Because Q is Grassmann odd, right? You can see this is Grassmann odd because C is Grassmann odd and e to the minus phi psi mu is Grassmann even. Right? So this is Grassmann odd. That's why I'm writing it as anti-commutator.
For Fermionic BRST exact operator.
It will be a commutator, yes. Exactly. Is this clear? Similarly, if this is a little more complicated to say, if zeta mu nu equal to k mu, let me call this u nu. Was there a u? Okay, at least if there is a u earlier, this u is different from any other u that I have. Okay, some vector u. Then, again exercise, V is proportional to QB with this should be sorry, no, this is not correct. I wrote the same answer, same result as this. Not that one. Let me read new. CCT. Okay, so this is that is that. Well, you can see what brings down e to the minus phi. You need e to the phi to bring down e to the minus phi, right? Because e to the phi times e to the minus 2 phi is e to the minus phi, right? So that term is gamma TF. Gamma has eta e to the f, e to the phi, right? So the gamma TF term will bring down, will produce this object. TF has a psi mu del x mu also, right? TF has a psi mu psi. So del x mu contracted with this will produce k mu, right? And the psi will be there.
Which is just k dot u.
Pardon?
There could be, I mean,
K.
evaluating the k, sorry, k dot u. So that if
No, not k dot u nu. K will not contract with u nu because u nu has contract with del bar, right? K will contract with another psi mu that comes from, because there is psi mu del x mu, right? So that psi, del x mu will bring down a K, right? And that will contract with the psi mu that is going to appear.
You're saying gamma TF is there in QB.
Yes.
So that will act on.
So gamma TF is eta e to the phi psi mu right? It has a term like this.
That is.
What? Eta will go with del psi, right? That will, it will pick up an OP. Okay, 1 over z minus w square. E to the phi with e to the minus 2 phi. Okay, will give you a z minus w square. That will kill that 1 over z minus w square. And this del x with this will bring down e to the I k over z minus w. Right? And that's what basically it produces this structure with psi mu nu given by this. Okay, you have to also make sure that the other terms don't give additional terms, right? There are two other terms which you have to analyze. Because Q has sum of 3 terms, right? I just looked at gamma TF term. K dot U has to be 0, right? Because that condition comes, yeah, K dot U is 0. Thank you. Because otherwise, the QB, the anti-holomorphic part of QB, right, will act on this part, okay, and will produce another term, right, which will effectively include contraction of K with U. So K dot U has to be 0.
What's the difference?
Difference between? Oh, because the left is bosonic, right is superstring, right? For the heterotic string, left side acts as if it's like a bosonic string, right? So it's simpler. Okay, so here the right side, right, the holomorphic side has been untouched, right? I've kept C to the minus phi psi mu as it is. Okay? And the C tilde del bar x mu to the I k dot x, right, that is generated by Q acting on this. Okay? Here it's more complicated because here you can see that the left hand side is untouched. There is C tilde U nu del bar x nu e to the I k dot x, right? That was there even here. Okay, there is C tilde del bar x nu e to the I k dot x, and for xi mu nu given that way, U contracts with del bar x nu. Right? So the anti-holomorphic part is kept unchanged, okay? But the holomorphic part, so you pick up the holomorphic part of Q, and that acts on this C del xi to the minus 2 phi e to the I k dot x to produce the term that we have there.
The first is it was CTM. That term was.
Yes, exactly. It's a CTM that produces the desired term. Here it is gamma TF that produces the desired term. Pardon? Yeah, C bar TM bar, yeah. Exactly. Is this clear?
Like, we can come from 2 different states. That's what we are trying to say.
No, these are different polarizations, right? In one case, it's K mu, V mu, K nu, right? So zeta mu nu I have not taken to be symmetric, right? Because zeta mu nu has both symmetric part and antisymmetric part, right? So if you want to project into symmetric and antisymmetric part, right, the graviton and the two forms, then you have to take a linear combination of this. Okay, the corresponding object will be a linear combination of this. Okay? But it is easier to not take zeta mu nu to be symmetric, right? Do separately for the holomorphic and the anti-holomorphic part. Is it clear? So this is telling us that these are pure gauge states. Okay? And now if we believe what is proved last time, right, that the boundary terms vanish, okay, then that means that amplitudes involving these will decouple completely from the S matrix. Answer will be 0. At any time, it's like if you have a longitudinally polarized photon, the result is supposed to be 0. No, longitudinally polarized, I mean k mu. Yeah, if you something proportional, if you take epsilon proportional to k, exactly, it's the pure gauge, right? So it's supposed to be 0. Right? If it's not 0, then the theory is not consistent. Okay. So similarly, here, if you really want to identify this as graviton, right? This is what we have been emphasizing, that we have seen that the spectrum is that of a graviton. Right? But that is not enough to prove that it is a graviton. Right? The interaction should also be like graviton. Okay? What this is saying is that the interactions obey the same properties as a graviton would, okay, or a two-form field would. Right? Namely, if you take a pure gauge state, it should decouple. Okay? And this is sufficient to guarantee that it describes general coordinate invariant theory. Right? But this is one of Weinberg's result, that if you have a massless spin-2 particle, right, and if it interacts with matter so that the longitudinally polarized parts decouple, then it is a theory of gravity. That it can have hard derivative terms, okay, but those are all generally coordinate invariant hard derivative terms in the effective action.
This is the pure gauge, and so if I mean all the states, all these kind of states will decouple.
Yes.
That means they will give the 0 amplitude or the scattering amplitudes.
Yes.
And then you're invoking Weinberg's argument of that there is only one possibility now, that it has to be only graviton.
That it has to be general coordinate invariant. That the action that describes such a theory must be a general coordinate invariant action. Right? That can be, it need not be Einstein gravity. Right? There may be R mu nu rho sigma kind of term in the action. But it has to be general coordinate invariant. And basically the idea is that this proves that the theory has gauge invariance. Right? And it has gauge invariance in an arbitrary amplitude. Okay? Yeah, diffeomorphism. Right? In an arbitrary amplitude. Okay? And that is enough to prove that it has full nonlinear diffeomorphism. Right? It's not just linear diffeomorphism, right? But the full nonlinear diffeomorphism is present in this theory.
What do you say about anything about, let's say, how gravity couples to other fields also, for instance, minimally or non-minimally?
No, it doesn't. It only says it couples covariantly, right? Because just based on gauge invariance, you cannot rule out non-covariant, the non-minimal coupling, right? So certainly there can be coupling of Riemann tensor to matter fields. Exactly. It doesn't rule out any such thing. Right? One standard coupling is RFF. Right? That kind of coupling can be there in this case. Yeah, G mu nu going to diffuse. Yes, B mu nu has. That gauge invariance, because it better have, right? Because here you saw two gauge parameters, right? So B mu nu is basically delta B equal to d lambda. Any p-form field has gauge invariance of this kind. Yeah, because then the dB is gauge invariant, right? And the kinetic term and the interactions occur through dB. Lambda is one form. It's clear?
It's a dimension independent statement.
Yeah, maybe 3 dimensions there are, you can add Chern-Simons terms and so on, right? Which are of course gauge invariant action, but not local gauge invariant Lagrangian. Okay? But yeah, so the action should be gauge invariant, right? That's the statement.
This one-form lambda is also some linear combination of.
Yes, exactly. Right. So one linear combination is the diffeomorphism parameter, right? The other linear combination is this one form lambda, right? Because there are two vector valued parameters, gauge transformation parameters, right? The diffeomorphism, local diffeomorphism is a vector valued function. Exactly. Exactly. Right? Difference is the B gauge field of the. gauge invariance for the B. Exactly.
Massive gauge. What does that do? Is it something similar in the sense? Like if you take a massive vertex operator.
Yes.
And then
Yeah, there is gauge invariance in that also, because QB, I mean, you can basically you can have massive, you can take QB on any massive vertex operator, right? Massive state. That's also BRST exact. So it will give a corresponding gauge invariance. Right? So there is gauge invariance at every level.
That is not very easy to see from targets.
No, because targets by writing down effective action for these is hard.
So that is some U1, right?
Okay, you don't call it U1 normally. Normally U1 refers to a scalar gauge transformation parameter, right?
What is that? This one, vector programming kind of.
It's a vector valued gauge transformation. It's abelian group. Right? What?
Lambda can be a two form.
No, lambda is a one form. Yeah. Yeah, that one.
So lambda is one.
Yeah.
But I mean, that's of completely different nature compared to diffusion.
Yes, it is. Right? But in string theory, they come on the together. Right? It's a symmetric and antisymmetric part of this gauge transformation.
This first to last about this massive case.
Hmm.
So we are not trying to write effective action for those fields, so that's why we don't care about it.
Yeah, but if you write a string field theory, for example, where the massive states also appear as fields, there you can see that the action has gauge invariance. It is not one of the familiar kind of gauge invariance that one is one sees. Well, that the whole thing is the gauge field, right? It transforms inhomogeneously, right?
But we have the corresponding like a Gauss constraint or in that case.
No, because there is no long range force, right? Exactly. So there is a long range force in that case. Okay. Now, let's look at the RR sector. Okay. And we take the vertex operator in the minus up picture. So take a V equal to zeta AB C C tilde e to the minus pi by 2 e to the minus pi tilde by 2 AC S tilde B. Okay. So this is supposed to describe some P form fields, right? 2A or 2B, this is supposed to describe some P form fields. This is for 2B. If it has 2A, then 1 will be dot. So claim there is no pure gauge state in this sector. Okay, so let me give the proof. That suppose B equal to okay. Yeah, let's assume that there is a state W for which V is QB W. This one has host number 1, 1. Okay, one from left, one from right. The way you have assigned host numbers, these don't carry host number. Okay, beta gamma does carry host number. Okay, but those come from xi eta. Xi eta, yeah. Okay. So we stay in the minus of picture. QB doesn't change the picture, right? So you stay in minus of picture. Okay. And if you stay within minus of picture, right, all the states in this sector are obtained by acting with either matter oscillators or BC oscillators or beta gamma oscillators. It doesn't change the picture number, right? If as long as you don't change the picture number, you can forget about the xi eta. You will only get states that are obtained from these by action of beta gamma, BC, and matter oscillators. Is that clear? Okay, so you have to look for W under that constraint, right? That we can apply on the vacuum, the Raman vacuum, either beta gamma or BC or matter oscillators. But that can be written down for beta gamma, right? Yeah, we are using beta, we are allowing beta gamma, right? We are just not allowing separately to the minus phi action. So W has host number 1, 0 or 0, 1. Okay. So compared to this, we have to reduce the host number. Okay. Now, reduction of host number requires that we apply either B or C, B or beta. Right? B or beta can reduce the host number. Right? We can also use something else with it, but B and beta can reduce the host number. Furthermore, it should have L0 equal to 0 and L0 tilde equal to 0. Because this has L0 and L0 tilde equal to 0, so and QB doesn't change the L0, L0 tilde quantum number, so it should have L0 equal to 0, L0 tilde equal to 0. Okay. So whatever oscillator you apply on this, okay, should not change the net L0 value. Okay. So if you raise L0, there should be something to lower L0. Okay. But you can check that there is nothing that can lower L0. Right? Because you already are in the host vacuum. CC tilde, right? Okay. In this sector, beta and gamma are integer moded. And if you recall, minus half picture has the property that all the positive oscillators annihilate it. Pardon? There's no lowering, there's no energy lowering of. Okay. So you cannot, if you increase L0, there is no way to come back. Okay. So you have to keep L0 equal to 0. That means you can only apply 0 modes on this. Okay.
Picture changing operator would not help.
No, picture changing operator you don't want to apply because picture changing operator will change the picture, right? QB doesn't change the picture, right? So you don't want to change use picture changing operator. SA, those are from the matter sector. SA, S tilde B are from the matter sector, right? Those are the spin fields of the matter, right? The host part is here. The CC tilde is coming from the BC host system, and these are coming from the beta gamma system, right? Or the xi eta phi system that you have taken the minus of picture vacuum. Okay. Equal to 0 because V has that. It's physical vortex operator, right? And Q commutes with L0 and L0 tilde. Okay. So the only possibility would have been beta 0. Right? Beta 0 of course is not GSO even, right? Beta 0 is not GSO even, but you could accompany beta 0 by a psi mu 0 because psi mu has 0 modes, right? The matter part has 0 modes, right? So changing the keeping L0 equal to 0 is not a problem. Right? The problem is to reduce the host number. Okay, if you could apply beta 0, it will be done. Okay. But beta 0 acting on the minus of picture is 0. Right? If you go back to your notes, you will find that on the minus of picture, beta 0 and beta tilde 0 gives you 0. Gamma 0 and gamma 0 tilde give you non-zero. But gamma 0 and gamma 0 tilde is of no use, right? Because that will increase the host number instead of reducing the host number. Pardon? B0 annihilates it. B0 and B0 tilde will annihilate it. So that's the proof. That W has to have host number 1, 0 or 0, 1 and no such states. No such state exists. Is this clear? Yes.
Heterotic theory only started off by introducing lambda.
Heterotic doesn't have this problem. This is Ramon. I'm considering now, for now I have left heterotic and considering type 2 or type 2B.
This was heterotic.
But I mean, you can easily generalize it to type 2 or type 2B, right? Because basically then the left and right will have the same. Right? That's all. Right? This psi mu, I mean, instead of C tilde del bar x nu, right? You will again write C tilde e to the minus phi tilde psi tilde mu. Right? And then both will have this structure.
Yeah, the bosonic part I just again replaced by Fermionic.
Exactly. The bosonic part will be replaced by Fermionic. That's the only difference. Okay. So whatever I have done in heterotic, I mean, you can repeat for type, right? This you should be able to do as an easy exercise, right? Just replace the bosonic part by Fermionic. But this issue that I am trying to point out now is not present in heterotic, but this is a problem in type 2. Okay, I'll say it's not a problem yet, right? I'll explain what the problem is. No, because this is SL2 or invariant vacuum. We start with SL2 or invariant vacuum, and we have only applied C and C tilde, right? So B0 and B0 tilde will still annihilate this. We have not applied any C0 or C0 tilde on the SL2 or invariant vacuum. B has host number 1, 1. Well, this again, some people count the other way. Some people will say -1, -1. Some people will say 1, 1. I'm counting C as 1, B as -1. Beta is -1, right? Because beta and B come together. Because QB, for example, has various terms, right?
Here there's still E to the I dot K.
Yeah, E to the I K dot X, yes. Thank you. And so this satisfies all the physical state condition, K square equal to 0 and so on. Now let me explain why this is a problem. Yeah, not yet. I'll explain now why this is puzzling.
No, only for gravitons you expect this pure gauge, right?
Yes. For B also we had a pure gauge. We explained why for B we need pure gauge because delta B equal to d lambda is a gauge transformation, right? Yeah, I have already told you these are P-form fields, right? P-form field. P-form. These describe Ramon fields, right? Massless Ramon sector fields describe P-form. Different P. I mean, depending on how P is. This one has zeta AB. This is a bispinner, right? So you have to decompose in the tensor representation, and it has various P's, right? For example, type 2A, right, would have a 1 form, 3 form, right, and they're dual. Okay? Type 2B will have a 0 form, right, which is the Ramon scalar, 2 form, and 4 form, right, with self-dual field strength.
So all of these are massless.
Massless. They should have a gauge invariance. And the gauge invariance for a P-form field is again just direct generalization of this. Delta Cp is d lambda P minus 1. We are not able to see this from here. That is, yeah, well, that's not a bad thing yet, but this is a puzzle, right? That if it is supposed to describe a P form, right, When you write a Lagrangian for the P form, right, it has a gauge invariance of this kind. Okay, delta Cp is equal to d lambda P minus 1. Okay, but you are not seeing it, right? Every polarization here is physical. Okay, there is no pure gauge state in this among these.
Is it possible that the gauge comes from other sector? But that will just mess up.
No, because all picture numbers are supposed to be equivalent, right? So the resolution is that R are vertex operators in minus half picture directly describes field strength and not gauge fields. Pardon?
Then, for example, if I take a practical calculation, for instance, let's say the target space level, I want to do theoretical compactification. Then you would say, don't do it at the level of gauge field, do it at the level of field strength of water.
Yeah, that's what it says. That it's like it's the way we first learn electrodynamics in terms of E and B, right? Not in terms of the vector potential. Okay? So what it is saying is that the zeta AB, right? When you try to reinterpret zeta AB as some polarization, okay, zeta AB will correspond to K mu Cp mu1 to mu p antisymmetries. So if Cp, okay, let me call it epsilon. Normally, if you have a gauge field, epiform field, right? Cp, its polarization tensor will be epiform, right? Antisymmetric P index object which is antisymmetric. Okay? So that's what we are calling epsilon P mu1 to mu p. When you try to make this correspondence between zeta AB and what you have in the polarization, zeta AB is directly this. Is this clear?
There are, if I look at just target space gauge fields only, so or the P forms, there is a difference between RR P forms and the P forms really coming from, let's say, other sectors.
Yes, yes.
And you think we should only treat P forms in the RR sector as only at the level of field strength. We should not think of
Exactly. Okay. Now, physically, what difference does it make? Right? Let's ask that question, right? Okay, you can always take a polarization, just photon polarization, right? And work with K mu epsilon nu minus K nu epsilon, right? Then that epsilon going to epsilon plus K, that gauge invariance will be automatic, right? Because it will just drop out from this K mu epsilon nu minus K nu epsilon, right? Okay. So what difference does it make? Suppose you chose to work with this kind of polarization. Okay? Is this question clear?
Yeah.
Why? What is the statement exactly? That this polarization zeta AB has to be of that form?
Yes. Yeah. The zeta AB, of course, is a bispinner. You have to decompose into the tensor representation, right? But after you take the appropriate linear combination by contracting with gamma matrices, right, to write it in terms of tensors, those tensors will directly represent these objects.
Some options there, like some P for P, like can be 1, 3, 5, 7.
Exactly. That's right.
And in each dimension, I want that.
You will have that combination. Pardon? Yeah, 10 dimension, right?
So you want SO9 tensor?
Yeah, that's what you're doing anyway. Yeah, you have to take the SO9 compound. How will?
KMU
KMU will not enter. Zeta AB, when you try to make connection with what polarization it represents, right, for the p-form fields, zeta AB should be thought of as that combination, this combination. That you will get zeta AB as linear combinations of some vector, right? Some tensor objects. What those tensor objects are, you don't know, right? You have to now connect it to what you will get if you had written effective field theory. Exactly, right? But if you take zeta AB and make this tensor decomposition, you will find not one form but two form. So what will land up is not one form but two form, four form, six form, etc., which reinterpret as these. Right? So a two form will not imply that you have a two form field, two form gauge field, but it will imply that you have a one form gauge field, because the relationship involves an extra k-mu.
How will I figure this out?
You will figure this out because if you didn't have this, then you would have to have a gauge invariance, right? So the only way to try to fit this into something that you understand, right, is by saying that the zeta AB should correspond to not the polarizations directly, but already the polarizations that appear in the expression for the field strength.
If let's say one tries to write down the terms of these sheets, then would you say that there are extra modes also, like longitudinal modes? Or you can't?
Yeah, then those modes will not decouple, right? If you think in terms of, suppose you try to reinterpret this as a two-form gauge field instead of a one-form, two-form field strength, right? Then that should have a gauge invariance, right? The DP. That those modes should then decouple, should have decoupled. But those modes will not decouple, right? Because those are not pure gauge.
Fail at the level of degree of matching.
Yeah, it will also fail at the level of degree, degree of freedom matching.
This is like, but in QFT, when we do some electron, positron, two photons, we put epsilon mu, not k mu epsilon.
Yes. So, but you could. Suppose you want to write a Lagrangian. Okay? And we had access to only field strengths. Can you write a Lagrangian? Sometimes, but not always. Yeah. So when can you write and when can you not write? The magnetic moment coupling, right? You can write psi bar gamma mu nu psi f mu nu. Right? That's the magnetic moment coupling. Right? Corresponding electric will have to have an epsilon, will have an f tilde mu, right? What are the terms that do not that you cannot write in terms of A mu J mu, right? So yeah, chance amounts is a little far-fetched. Just A mu J mu, right? Psi bar gamma mu psi A mu. That you cannot write, right? So this is saying that if this is true, then certain terms you cannot write. Exactly. Okay, that there is some certain terms that you cannot write. Okay, which involves the fields rather than field strengths.
The effective target Swiss action, they will not appear.
They will not appear, right? So those are the terms, right, which describe coupling of gauge field to charged particles, right? For neutral particles, if you have an electromagnetic field, for neutral particle coupling, right, there will be through magnetic moment, the magnetic dipole moment, electric dipole moment, higher magnetic moments, higher electric moments, those can all couple to field strength. So all those couplings you can write.
Does that mean that other fields cannot couple to, let's say, charge scalars?
No, that RR fields, yeah, who's a charge under the RR field, right? That this is basically telling us that string theory, elementary particle spectrum in string theory, does not have any state that carries RR field, RR charge. They're all RR neutral. Pardon? Yes. P form. Exactly. Right? But the coupling will always be through this combination. Yes. Yes.
Only coupling through moments and all.
Yes.
I can describe photon and other scattering.
Yeah, all the interaction terms you can write in terms of the F mu.
Scattering process, I can write
in principle you can. Yeah. Exactly.
Epsilon by itself.
Yeah, exactly.
This
Yes.
will see when we decomposed. So we'll get this as 2 form, 4 form. Then we'll
Yes.
decide that okay, we have some 1 form field.
Exactly. Exactly. Right. Whereas for type 2b, right, you will find that when you take zeta AB and decompose it, right, you will get 3 form, 5 form, right, 1 form, and so on, right, which you have to re-identify as D of the corresponding fields, the gauge fields. Here, this is all are biastic closed. Yeah, all zeta AB give biastic closed states.
But this is very different from this, it seems. Because there we saw that the B field, the fourth for B field, this B lambda, the lambda was related to these operators.
Exactly. Yeah.
But here it seems like it's D lambda. We are saying that it's a D of something.
Yes.
Field, but even then it's not BRST exact.
No, it's what is not BRST exact? Yeah, that so you, if epsilon was D of something, then this will vanish identically, right? Yeah. So the fact that a pure gauge states decouple is trivial in this language. If you only couple to field strength, right, then obviously pure gauge states will decouple because field strength is 0 for pure gauge states.
But the D had a correspondence with QB there.
Yes.
But here it's not true.
That's true, yeah. Exactly. So these D doesn't come from QB.
Some K 1 times something, then it is trivial 0.
Yeah, then it's trivial 0. Exactly. Right? Then the zeta AB will be 0. Right? Not that there is some particular zeta AB which will decouple.
D on that.
D on this? Or D on zeta AB?
It's like multiplying with a K. And that's what you are saying. Contracting with a K. And that's what you are saying is identically 0.
Yeah. DF is 0, right? Because if F is DC, right, then DF is identically 0. Is this possible? Is this clear? Right? So there is no elementary string state that carries Ramon charge. Pardon? Type 2 theory, yeah. Ramon fields only appear in type 2 theory, right? Now, this suggests that you cannot get any Ramon charged objects. Okay, and this is what was thought for many years. Right? When this duality was discovered, then people figured out that if duality is true, then there better be Ramon charge objects, right? Because duality implies that there should be Ramon charge objects. Non-perturbative duality, right? The duality, for example, that relates, one of the simplest ones is type 2b in 10 dimension has an SL2Z duality, right? Which exchanges fundamental strings with a Ramon charge object. Because there is one 2 form that is coming from the NS sector, right? The B mu nu, and there is another 2 form that is coming from the RR sector. Okay? The SL2Z, the G goes to 1 over G part, exchanges those two. Right? So if there are objects that carry fundamental string charge, right? String certainly carries B mu nu charge. Right? Then there better be object that carries B prime mu nu charge. Okay, and then D-branes basically solve that problem. Okay? D-branes do carry Ramon charge.
You said some statement that we cannot have charged objects
under this.
Tower.
Yes.
Why cannot I?
Because in all couplings, right, you don't see any pure gauge state, right? There is no way to describe pure gauge state in the spectrum.
Okay.
Right? So then the fact that those states decouple is not is a trivial statement, right? Because pure gauge states are trivially 0.
If there is some field corresponding to any of these states here, which
I can write a term in the action which contracts with that, right? The P form P.
With CP, right? But the problem is that CP doesn't exist because the 3-point vortex, when you calculate the 3-point amplitude, right, it directly couples to not C but DC, right? Whereas if you want a object that is charged under the Raman field, right, it has to couple to C, not to DC. Right? That's the main difference. Electrically charged the charged objects versus uncharged objects, right? Uncharged object coupling can only be written in terms of field strength. Right? The charged object coupling requires field, the gauge fields themselves, right? They cannot be written in terms of field strength. Pardon? Yeah. It's called, everything is called S duality, yeah. Yeah. Anything that has SL2Z is called S duality somehow.
Why are you calling it G goes to 1 over?
But there is also, it extends to SL2Z, right? Once you, because there is a Raman scalar also, so that combines with the delay on coupling constant to a complex coupling, right? Like tau. Yeah, you can think of G as a complex number. G itself is not complex. The complex combination is 1 over GS plus that I times that scalar. I times scalar, right? Raman scalar. Not dilaton is the GS, right? Is a GS, right? But there is also another scalar which comes from the Raman sector in type 2 theory. One of these, yeah. One form field strength. P equal to 0 in that language. Type 2B. Type 2B has a 0 form field. Yeah. Only in type 2B. Yeah. So this statement is only in type 2B.
So this specific duality is state 2.
Yeah.
But then you're saying that there exists a duality between type 2 and type 2B also somehow.
Then you after compactification.
Like RR charged object can't be this kind of this whatever we get from quantizing this.
Fundamental string. Yeah. Exactly. Exactly. Yeah.
But then, at any point in history, does it suggest that we should treat these different object elements should be as elementary also?
Yeah, it does. I mean, as long as they are finite mass objects, right? They're as good as elementary particles.
And by, I mean, from get-go, I mean, from the starting, we just don't write the Polya collection, but they change at that level so that we can.
Oh no, that we cannot do. At least nobody has been able to do that. You are thinking of the
I mean, we can get the manifestation of
S duality.
S duality by just changing the
Yeah,
level of
if you could do that, then it will give manifest S duality, but nobody has been able to write a consistent theory in that form. Yes. Yeah. Okay. And the way the D-branes avoid this problem, right? That how does it couple to field, other field strength? Okay. So the first point is that this argument that there is no gauge field, that there is a pure gauge state, breaks down if you work in the -3 of minus up or minus of -3 up picture. -3 of take -3 of minus half. Okay, or minus of -3 half. Okay. There, either in the left or the right sector, okay, beta 0 doesn't annihilate the state, annihilate the vacuum. Gamma 0 annihilates the vacuum, right? So you can apply beta 0, right? And then QB on that will produce the original state, which is pure gauge. It's a picture number dependent statement. Whether you can admit a pure gauge state or not is a picture number dependent statement. In the -3 of picture, you can have pure gauge state.
Homology is same in all.
Homology is the same.
But that means there should be same number of BRST closed states.
There are. Right?
There are extra BRST.
It just has more physical states, right? And then you have to remove them because some of them are BRST closed.
Exactly.
BRST exact.
In a different
number, you can have BRST exact state.
Exactly. In a defined picture number, you can have BRST exact state. That's the statement.
Okay, the representative is like this only, no? So you just take the half to 3 half.
Yeah, but there are other states, right? Including in which involves hosts. Beta gamma host system, right? Yeah. Yeah. Exactly. Exactly. Right?
So you have to identify the BRST exact so that homology matches.
Exactly. Cohomology will match, right? At a generic momentum, cohomology matches. That is a theorem. So the point is that because of this, right? If for some calculation you are forced to use minus 3 half minus half picture or minus half minus 3 half picture, then it may be that the gauge field will appear explicitly in the coupling. But you have to be forced to use that, right? Because the amplitudes are independent of the which picture you use, right? So only if you are forced to use minus 3 half minus half, right, that you have a hope that maybe it will have a non-zero coupling to the gauge fields rather than field strengths.
This is anyway like, I mean, at some point you're saying that these deviance can be treated as elementary factors, right?
Yes.
And so forced to be does not make sense, right? Because now they are really elementary particles.
But the calculation is different for those.
Yeah, I mean, some
Right?
calculation they won't be required anymore. Right? As far as you're saying amplitude calculation goes of the strings.
Yeah. But the rules are different, right? The way you will calculate the amplitudes will be different, right? So when are you forced to use minus 3 half minus half, right? And that happens if you have a disk one-point function. Disk one-point function. Take a disk with D-brane boundary condition. Okay. One-point function, okay, on a disk, the total picture number has to add up to minus 2 from left and right. Disk has a boundary. Sphere has minus 2. Sphere has minus 2 on the left, minus 2 on the right. On the disk, the total picture number has to be minus 2. That on a disk, you don't distinguish between left and right because the boundary condition relate left and right. Right? The total picture number, so there you count only total picture number, which has to add up to minus 2. Okay? And minus half is not going to do, right? Because minus half will give you minus 1, and picture changing operator only raise the picture number. Right? So you are forced to use minus half minus 3 half, okay? And that you can check gives you a non-zero answer for appropriate boundary condition. Minus 3 half you can use, and you have to use picture changing operator. Yeah. 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 So lower ones do, right? The higher ones don't.
Now the statement there you are forced to use minus 3 half.
Minus half. And then you can explicitly check that the zero momentum coupling is non-zero. See, these things have the property that if the coupling is only through this combination, right? There is no zero momentum coupling, right? Whereas the coupling to charged particles is a zero momentum coupling. Yeah, so here the soft photons will just decouple. Right? It will not produce a pole, or the analog of the soft theorem for these objects. Well, you can have higher order soft theorem, but not the leading soft theorem. Yeah.
But in this one-point function, you will see low momentum.
Yeah. So if you have B branes in the external state, then you can have the regular soft theorem. Because D branes do carry Raman charge, and they will produce a standard soft factor.
How? What's the insertion?
This one-point function,
Yeah.
vertex, Raman vertex operator. Yeah, this in the minus of minus 3. This will the gauge field rather than field strength.
And is there any way that, I mean, the same thing can be, let me do it at NSNS level, for instance. I can try to construct a vertex operator with some with different. I mean, vertex operator such that I won't have this. I won't have pure gauge in the NSN sector. Basically, what I'm trying to say, you can't write them in column on P, but instead you can have only DP.
See, in a sector, the massless fields are all very completely classified, right? So you can't really do much with those. And the P coupling, we know, comes from here.
I thought the problem is that this theta AB, we are interpreting that as field strength. And if I'm
Yes.
saying that that thing has a non-vanishing this 1 point function, this means it's again field strength times the
Yeah. So, yeah, exactly. So that's in minus of picture. In the -3 of minus of picture, zeta AB will be related to not field strength but field. Right? Because there you have pure gauge states. Right? And you can easily check that the zeta AB there will be related to field. Right? See, one way to check this, one way to see this is that suppose you go to -3 half, right? In 2B. Suppose you go to -3 half. That means you are applying a e to the minus 5, which is a GSO odd operator, right? You cannot just apply e to the minus 5. Okay? So you have to apply e to the minus 5 and the psi b. Okay? The psi will change this index to a dot index. Right? So in the -3 of picture, you have e to the minus 3 5 by 2, and this will be S A dot S tilde b. Okay? When you decompose that in tensor representation, right, you exactly get the ones that you miss here. Okay? So here, if you get, suppose you are working in type 2B, right, you will get 1 form, 3 form, 5 form, which you identify as a field strength. Okay? In -3 of minus of picture, okay, you will get 0 form, 2 form, 4 form that you interpret as field, not field strength. Because the tensorial property will change, right? Because once you change the A index to A dot index, right, the tensorial property will change. Okay, so that's another way of saying that if one gives field strength, the other one will give field.
But in both cases we have extended, we have objects which is in one case charge under this field strength and other case charge under fields.
Yes.
But both of them are called d-branes, or we have to distinguish between?
No. The ones that are charged under field strength, they are not really charged, right? They carry dipole moment kind of thing. Right? So those are not d-branes. Ordinary particles can have that property, right? That it can carry dipole moment of a Raman field, but not charge under the Raman field. Right? But it's not that the Raman field decouples completely, right? They do have some coupling. They appear in the S matrix, right? So they better couple to these ordinary particles. Yes. No, but you are forced to use -3 of minus half only when you have d-brane. See, otherwise you can use -3 of minus half, right? You will be happy, okay, now you have a field, right? You have a pure gauge. But what you will find is that the final coupling when you get, right, it will always involve a combination of DC. Because if the results in the various picture numbers are the same, right, then if the coupling involves DC in one picture, it involves DC in any other picture number, right? It's easier to see in the minus of picture rather than in the -3 of minus of picture.
Like this, that -1/2 we can never access the non-productivity or like d-branes -1/2.
Well, see, most you can the scattering you can calculate using this, right? It's just that if you want the 1 point function, right, that one amplitude you cannot get using minus of. Yeah, this 2 point function you can use minus of. From the but from the d-brane perspective, it's actually a 3 point function. Coupling of one external particle. See, d-brane is sitting there, right? The d-brane doesn't disappear. It's not like you don't directly interpret this as a scattering matrix. You have to do some work to reinterpret this as a scattering. And that is basically one d-brane coming in you have a one-point function and the same D brane goes out. So this one-point function for the on the D brane has that interpretation.
So what it will be as a scattering, what will it
As a 3-point function of D brane gauge field.
So in the minus half picture number, the whatever the vertex operator, so we don't say that is charge, we say that the D brane is.
Yes, that's right. Yeah, vertex operator is not charged. It's a D brane that is charged. Exactly. That is the one that carries Raman charge.
That we say because of this understanding that in minus half picture we don't have any like elementary state that is RR charge.
Exactly. So no elementary state is RR charge. Right? It's only D branes that can be RR charge.
So even if we calculate in minus half picture number, the vertex operator that will be, even if we calculate any other say correlation function of that operator, we will not see that.
Exactly. Right? It's not obvious in that picture because you do have vertex operator for the C, right? But only after you do the calculation, you will find that it's not charged because it always comes in this combination. That the way the polarization enters, the answer is always in this combination. Right? And that follows because in every picture number you should get the same answer. Is this clear? Okay, so we have to discuss the boundary. But before I discuss the boundary, maybe I should just discuss one more point, okay, which has nothing to do with what we discussed so far, but it's related to the other result that we found. That is independent of the result is independent of the choice of section, right? Again, up to boundary terms. Okay, so SGMN and S prime GMN give the same result. This tells us that we can generalize our choice to not just sections, but what are called chains. That so this implies that half of SGMN plus S prime GMN give the same result. Okay. Or more generally, sum over I, Wi, Si, GMN give the same result. If sum over I, Wi equal to 1. Okay. Where this basically means, okay, what does it mean? S is a section, right? What does it mean to say that we take some fractions and take sum over sections, right? Weighted sum. Okay. It means basically that while as a manifold, it doesn't make sense to take sums like this. That integral sum over I, Wi, Si, GMN of omega GMN 6G minus 6 plus 2M plus 2N is by definition sum over I, Wi, times integral SI GMN Okay, this is what it means, that if you integrate over weighted sum of sections like this, right, that basically means that it's this. Okay, it's the weighted sum of the integrals. And now, because everything is independent of choice of the section, I can write this as integral over S GMN of omega GMN 6G minus 6 plus 2M plus 2N. And then use the fact that sum over IWI is equal to 1. Okay, because now that this is independent of I, right, you can just use sum over IWI equal to 1 and get back that original answer. Is this clear? Right? So this is sometimes useful, that we don't need to take the picture changing operator, right, a single section, but weighted sum of sections. Individually, yes. Okay. And sometimes it's useful for, I'll give you one example where it's useful. Let's take 3 NSNS punctures on the sphere. Right? 3 NSNS punctures on the sphere, you put say 0, 1 at infinity, okay, and you have to insert another picture changing operator. Now 0, 1 and infinity, right, there is a symmetry that permutes 0, 1 and infinity, right? Part of SL2Z, SL2R symmetry, or SL2Z symmetry you can use to permute 0, 1 and infinity. Okay. And for some purposes, if you want to make that permutation symmetry manifest, okay, you may want to choose the picture changing operator to be invariant on the permutation symmetry. Right? So you need to find a point on the sphere or on the plane, right, which is invariant under any SL2C transformation that permutes the 0, 1 and infinity. Right? This is a 6 dimensional group, right? S3. Is that clear? Right? I'll give you the example, right? What are the generators? If you take on a sphere at 0, 1 and infinity, right, then this is invariant under, first of all, Z goes to 1 minus Z. Right? What it does, it exchanges 0 and 1 and leaves infinity unchanged. Right? Z goes to 1 over Z. This exchanges 0 and infinity, leaving 1 unchanged. Right? And then you can just combine them to generate other elements of the group. Okay, because the permutation group, once you have got the 2 exchange operators, you can just combine to generate the 6 other. And you may want to find a point that is invariant under these transformations. All of them. Yeah, and if you use this to generate, right, then it's enough to know that it should be invariant under these and this. So there is no Z which does this, right? So then the next best you can hope for is to find a pair of points which are exchanged under this, right? Because, and then you can take half of the picture changing operator at the first point plus picture changing operator at the second point.
But the S3 symmetry will be manifested in the end.
Exactly. S3 symmetry will manifest at the end. Okay. For physical part, vertex operator, of course, it doesn't matter because the result is independent of choice of the picture changing operator anyway, right? But it's often useful when you are trying to formulate string field theory, for example, to use symmetric vertex of this kind. Is this clear? Right, so this is one of the uses of this, allowing this more general class of choices of sections.
That at the level of correlation function you want to make that statement, but do you want to interpret this also? Because this summing over sections.
No, this is just a formal object. No. This is just a formal object, right? All it means is, so if I say that I have chosen a section like this, right, what it means is how to calculate a correlation function, right, with that choice. right? Because the sections you are going to use to integrate over those sections. Okay, so now in the last few minutes, let me just start at least a discussion on boundaries. Okay, next time I'll try to finish it. Okay. So you have been talking about having to deal with boundaries because those integrals may have boundary terms, right? And all our analysis assumes that there are no boundary terms left over. Okay. So what are the boundaries? Okay. Boundaries are basically degenerations of the Riemann surface. And there are two types of boundaries, both of which can be dealt with at the same using same technique. One is separating type. Where a neck pinches off. Where a neck pinches off of the Riemann surface, right? And it's separating because once you pinch it off, then it becomes two separate Riemanns. The other one is non-separating type. Where even again a neck pinches off, okay? But even after you pinch it, right, if you separate it out, the resulting Riemann surface remains one. Okay, it doesn't become two separate Riemann surfaces. Is this clear? Right, locally it is, the structure is the same, right? So on a torus you can think of these two different degenerations in the following. The one is that you have a torus with some vertex operators, okay? And you just take the A cycle of the torus and make it small. Okay, then the A cycle pinches off, right? The torus gets cut. Okay, it becomes a sphere, but you are left with a sphere with all vertex operators, right? Imagine there is a torus cylinder, right? So torus. You have vertex operators, you just pinch one cycle. The other one, again, take a torus with vertex operators. Okay. Now you take part of the torus, so I have to say there are a few vertex operators inserted, okay, and pull it out and pinch it. Right? Then it becomes you pull out that part, right? It becomes like a balloon, right? And then you pinch the neck of the balloon. Then it becomes a sphere plus torus. Right? That's the separating type degeneration. Okay? But both involve pinching necks. Pardon? No, sphere has no boundary. When the modular space of sphere has boundaries. Modular space of sphere, the boundaries of the modular space of spheres are when you pinch a sphere, right? With some vertex operators on one side, some vertex operators on the other side, right? It goes into two spheres. Yes.
Can you explain in this keyhole diagram what do you mean?
Keyhole diagram is only one. So in the keyhole diagram, you can explain the non-separating type, right? Which is tau goes to I infinity. Yeah, tau goes to I infinity, normal hunk of one cycle becoming large, but that's equivalent to saying the other cycle is becoming small. So that will correspond to a separating, non-separating time degeneration of the totals. No, the other kind is also there. If you have vortex operators on the totals, right? Then when some vortex operators come together, that's the separating time.
You mean in M1, n? With punctures, you should.
With punctures, yeah. Yeah, with punctures, when some punctures come together, then that becomes a separating time degeneration. Because that is equivalent to, but that can be conformally mapped to a sphere where the punctures are there and a small neck is pinching off in the sphere. Is this clear? You can also think of it in the following way, that if you have, say 4 operators are coming together, right? Then you can use OP to replace those 4 operators by one operator, right? So it's as if there is a one, instead of having a 4-point function, right, you have a 1-point function, and then the other part is the 4-point function, 4 operators on the sphere and another operator on the sphere, because OP basically is a 5-point function on the sphere, right? OP of 4 points coming together is like the 5-point function on the sphere, right? So that's the pinching, right? One neck gets pinched and then you have 4 on one side and 2 on the other side. Is this clear? Okay, so I'll finish by describing how to coordinatize the boundaries, right? And then later on, next time we'll see how to actually analyze the boundary contribution. Okay. So suppose you are near a pinching like this. Okay, let's take separating time for definiteness, but the same idea works for non-separating time. Okay. So the first question is that near the pinching, how will you coordinatize? How to properly choose coordinates where you can understand what the integrand will look like, right? Because you have to understand what the integrand looks like if you want to understand whether the boundary terms are 0 or non-zero, right? So you want to know how to coordinatize the region near the boundary. So choice of coordinates near the boundary. And here is the way we choose it. Yeah, so imagine that we start from the other side where they have already been separated. Okay, if they're already been separated, then in the separated surface, right, we have all the original punctures, but one extra puncture on each, right? Because that's where the handle got pinched, right? So the original punctures plus one extra puncture on each surface. Is that clear? Okay. So let's call this Z1 and Z2, or say Z1 prime. And let's choose some local coordinate system, okay, which we call W1 and W1 prime. Okay, these are the local coordinates. So W1, W1 prime are local coordinates. These are the coordinates in the measured in the coordinate of the one surface, right? And W1, so for example, the Z equal to Z1 will correspond to W1 equal to 0, right? And Z prime equal to Z1 prime will correspond to W1 prime equal to 0. Right? So you can take for example, W1 to be Z minus Z1, right? But you can take some other functions which vanishes at Z1. Okay, the final result is not sensitive to how you choose this W, right? You choose W's in some way. Then we identify W1 prime equal to Q.
This could be any number, right?
Yeah, this is a complex number. It's not picture number or anything. Yeah, this is some complex number.
Right now, what this is a three parameter or you will here. While doing this, we have to do something new.
Yeah, so Q is a free parameter right now. Okay. And now I'll give the claim. The moduli of the individual Riemann surfaces together with Q give the moduli of the glued Riemann surface and Q goes to 0 is the degeneration of the glued surface. So physically, let's see what we are doing, right? So we have W1, W2, W1 prime equal to Q. So this means that you are taking, say, a circle mod W1 equal to mod Q to the half, and another circle mod W2 equal to mod Q to the half, and identify those, right? You are basically putting them together. Because on that circle, W1 equal to mod Q to the half will imply W1 prime equal to mod Q, right? As Q becomes smaller and smaller, that circle that is being glued becoming smaller and smaller, right? That's the pinching. In the Q goes to 0 limit, it pinches. Is clear? Right? So then Q is the parameter that you can use for describing the normal to the degeneration, right? So when you are talking about boundary terms, okay, is the boundary term in Q. Okay? Q equal to 0 is the boundary in this language, right? And you have to try to ensure that there is no boundary term from Q equal to 0. Is this clear?
Once you take it to 0.
Exactly. So if you take a total derivative, right, then the integrand should vanish at Q equal to 0. That's the statement. Okay. Let me just end by doing the counting. That we have got all the parameters. So let's suppose that sigma 1 has genus G1 and M1 plus N1 functions. And sigma 2 has genus G2 and M2 plus N2 functions. So total number of parameters
The moduli space dimension.
exactly. We're trying to see if the moduli space dimension matches, right? Because we said that the final Riemann surface is coordinatized by the moduli of the original Riemann surface and Q, right? But to make sure that that is everything. right? Or that we have not overcounted. Yes, indeed. So I'll subtract it out, right? So sigma 1 then has 6g minus 6 plus 2 m1 plus n1, right? This is coming from sigma 1. Sorry, g1. Then 6g2 minus 6 plus m2 plus n2. 1, 2 m2 plus n2. And then there are two more. Q is complex parameter, right? Plus 2. This is from Q.
That's M1 insertion you should think of as a function.
Yes, you should.
M1 includes that.
M1 includes that.
After the identification, think of as.
Yeah. So after the identification, so this is genus G1 plus G2, right? That is clear? Minus 6. How many punctures? M1 plus M2 plus N1 plus N2 minus 2. Because you lose one from each, right? One puncture from the first Riemann surface, one from the puncture from the second Riemann surface goes there, so minus 2. So are these equal? So there's a minus 6 here, right? And plus 2, that's minus 4. Right? And here minus 6. 1 minus 6, of course, is all there. And then this 2 times minus 2 is minus 4. So these two are really equal. Okay? So this shows that you have got the right number of parameters, right? You don't have to add anything else. Okay, so when you glue like this, take the moduli of the original Riemann surfaces and add this parameter Q, and that gives a correct parameterization of the combined Riemann surface. So next time we are going to use this picture to figure out how the integrand behaves near the boundary.
Always go to this lower out of one modulus space you have to split it into.
Yeah, exactly. Right. So that those are the boundaries which you have to deal with.
Like those two types of.
Yeah. So this is a mathematical theorem that the only degenerations of a Riemann surface are of these two types, separating and non-separating, but both can be handled exactly in the same way, right? Even for the non-separating type, it's exactly the same. You just have to add the Q as the extra, right? The counting is somewhat different because there the initial surface before degeneration, if it had genus G, then the final surface will have genus G minus 1, right? Because we pinch a handle, right? But we are adding two punctures. Exactly, and the parameter Q. And you can easily convince yourself that it gives the correct counting, even in that case. Okay. So then we'll have to see whether using this parameterization we can prove that the boundary terms vanish.
For on cell and BRST exact. For others, can contribute or can never contribute.
Yeah, so when you say boundary terms vanish, right? It's only for total derivatives, right? The boundary terms make sense, right? But I'll give a general procedure of how to integrate near the boundaries. Right? That will be independent of the whether you have BRST exact or not. And then using that general prescription, we'll see how you can prove that the total derivatives will get zero contribution from the boundary. Okay, so I think I'll stop. Whether Jyotirma did that work finally or it's still that